Hello everyone, myself Manjunath Reddy from 7th Sem Mechanical Engineering. Today I am going to present the experimental learning component for the course Robust Design. I have chosen the topic as laser etching experiment. This work is done under the guidance of Dr. Bharti sir. In this presentation, we are going to cover introduction, objective, apparatus, procedure, tabular column, experimental design and methodology, analysis procedure, results. Laser etching. Introduction. The study analyzes the effect of power, which is in terms of percentage, scanning speed in terms of millimeter per second, and frequency in terms of kilohertz on the width of laser etching, which is measured in the terms of micrometer in a laser etching apparatus using statistical analysis method. The goal is to determine how these factors influence the system's response. Laser etching machine is a device that uses focused beam laser beam to create permanent marks or design on a material surface by selectively removing a thin layer of material through heat, essentially etching the desired pattern onto the object, allowing for precise and detailed markings on various materials like metals, plastics, and glass, often used for applications like product labeling, branding, and create intricate designs. Objective of this experiment is to develop a regression model that predicts width of each based on the factors which affect this each. Those factors are power, scanning speed, and frequency. To analyze the significance of power, scanning speed, and frequency and their interaction using ANOVA. This study is important because it helps in optimizing etching process by understanding how power, scanning speed, and frequency affect time, reduces experimental effort by using statistical modeling to predict etching behavior. Apparatus. Apparatus is apparatus used for this experiment is shown here. Objective is to measure the width of each in a laser etching machine under varying power, scanning speed, and frequency. The apparatus used includes laser etching apparatus, EZ-CAD software, electronic microscope. Procedure for this experiment: entering the parameters in the EZ-CAD software, forming the laser etching operation, taking the images of the etched part and the electronic microscope, measuring the width of each from the images. The etching of the etching of the metal part has been shown in the image, where we have etched as a line for using different parameters. This is a tabular column which gives us the width of each for different power, speed, and frequency. Power in percentage, speed in millimeter per second, frequency in kilohertz, and width of each in micrometer. Experimental design and methodology. The setup used for this is laser etching machine. The factors considered are power, scanning speed, and frequency. Power has three levels: 50%, 70%, and 90%. Scanning speed also has three levels: 300 mm per second, 600 mm per second, and 900 mm per second. Frequency is under two factors, which is 25 kHz and 50 kHz. So the design summary is that three factors, three power levels, three scanning speed levels, two frequency levels, 18 runs, one replicate, and one block. Methodology: vary all the parameters and measure the width of each. Apply regression analysis for prediction. Use ANOVA to access factor significance and interactions. Access factor significance and interactions. Objective is to optimize etching width by analyzing factor effects. Analysis procedure: full factorial design in Minitab. Open Minitab and create a factorial design. This analysis procedure can be now shown in Minitab. Opening the Minitab software, this is the interface we can see. To start with the analysis of our experiment, we can click Start, DOE, Factorial and Create Factorial Design. We are choosing General Full Factorial Design and the number of factors are 3. And in the designs, we are changing the name of the factors from ABC to the actual factors. The factor A is power in percentage. The factor B is scanning speed. In millimeter per second. The third factor is frequency in kilohertz, and the number of levels are 3 levels for power, 3 levels for scanning speed, and 2 levels for frequency. Number of replicates is kept 1 because we have conducted one experiment for one factor level. If you are conducting two or more replicates experiments for one factor level, then we can change the replicates. Click on OK. And in design, factors, you can change the factor type as numeric or text. In this experiment, all the factors are numeric, so we click on OK. Options, check that randomize runs and store design in your sheet and click on OK. Results, check that summary table is clicked and click on OK. OK. Here, design summary is found, and now we can see the table here with power, frequency and scanning speed. These are randomized, so to get it in order, we paste the experiments here. Copy all the factors and paste it in Minitab. Now we copy response and paste it in Minitab. To continue with analysis, we click on Start, DOE, Factorial, Analyze Factorial Design, and select width of each and click on Select, and select on terms. Select all the vectors and click on OK. Covariates OK. Options, select no transformation and click on OK. Stepwise, select none and click on OK. Graphs, we are plotting 4-in-1 graphs and also residual versus variables and click on OK. Results, check simple tables and click on OK. Storage, select fits and residuals and click on OK. Again click on OK. Now we can find the values of fits and residuals here, and also the ANOVA table. ANOVA table, model summary, coefficients, regression equation, fits diagnostics and usual Pareto chart, and residual plots for width of each. Now to continue with the analysis, we again click on Stat, DOE, Factorial and Factorial plots. Now power, scanning speed and frequency all are selected, and we have to change the terms to display to all terms. And in options, nothing changes, OK. And in graphs, we check that main effect plots and interaction plots are ticked and OK. In view model, power width of which is the response and close and click on OK. Here we can see the main effect plots and the interaction plot. These are the results we got from the Minitab software. After the analysis of in the Minitab software, the first column shows the standard order, which is in the randomized, and the second column shows the run order, and prototype, blocks, power, speed, frequency, width of pitch, fits and residuals. Here, in the next slide, we can see the factor information, which says that the what in which levels and what are the values of the levels for the different factor. Here we can see that power is in three levels 50, 70 and 90. Speed in three levels 300, 600 and 900. Frequency in two levels 25 and 50. Now we can see analysis of variance, which is also called as ANOVA table, which says that error degrees of freedom for errors is 12 and the SS adjoint is 266.753. In the model summary, we can see that R square value is 70.25%, which is acceptable. Coefficients can be seen in the next column and the regression equation for the width of each. Here we can see a Peruta chart of the standardized effects. Here in the x-axis we can see the standardized effect and the y-axis we can see the different factors. A represents power, B represents speed, and C represents frequency. This chart shows that A has more effect compared to B and C. These are the residual plots for the width of each in mm. Normal probability plot, fitted value versus fits, histogram, and versus order. Main effects of plot for width of each in mm. Here we can see that as the power increases, the width of each also increases. As the power speed increases, width of which decreases. Frequency doesn't affect the width of which as compared to power and speed, but it slightly increases the width of which with increasing frequency. Here we can see the interaction plot for width of which. The first image shows the interaction between A and B, and the second between A and C, and the third between B and C. Conclusion: the experiment used full factorial design in MATAB effectively analyzed the impact of power percentage, scanning speed in millimeter per second, and frequency in kilohertz on width of which. The ANOVA results confirm that these factors significantly influence the response with a p-value of 0.00, indicating strong statistical significance. The regression model with an R-square value of 70.25% provides a reliable predictive equation for estimating width of each. Observations from main effects and interaction plots reveal that increasing power generally increasing width of each. Increasing scanning speed decreases the width of it, while increasing frequency does not have much effect on the width. Residual analysis further validates the model's accuracy. The study highlights the importance of optimizing laser etching process parameters to enhance accuracy of each, making this approach highly valuable for precision manufacturing applications. Thank you.